Hello and welcome to this second presentation related to gyroscopic motion. In the first presentation we introduced the concept of precessional velocity labelled as omega p, which for example relates to tilting of a rotating rotor. In that presentation we derived the equation for gyroscopic torque. T is equal to I multiplied by omega p, where omega is the angular velocity and I is the moment of inertia. I is mk squared. In this presentation we're going to use that knowledge and now consider an array of exercises in which we will be calculating gyroscopic couples or gyroscopic torques. It is assumed you've seen the previous introductory presentation before reviewing these exercises. This presentation consists of 5 separate exercises, and within each we're going to determine the gyroscopic torques and the associated effects that are induced. Exercise 1 relates to a ship pitching bow down, stern up. Exercise 2 relates to a ship travelling in a circular path. Exercise 3 relates to a bike travelling around a flat corner. Exercise 4 again relates to a ship with rise and fall motion. And exercise 5 relates to a flywheel subject to a precessional velocity, in which we calculate the gyroscopic torque and thus the reactive inertia torque, and from this we can determine the forces on the 2 bearings that support the flywheel on the shaft. And here are the approximate start times related to the various exercises contained within the presentation to hopefully aid your ease of access through the presentation, but please note these times are generally rounded to the nearest minute. There are a couple of questions left for you to attempt at your own pace, and they commence 32 minutes into the presentation. Exercise 1. A ship has an engine that rotates clockwise when viewed from the front, or from the bow. The engine has an effective moment of inertia of 250 kg/m squared and rotates at an angular velocity of 400 revs per minute. We're asked to calculate the magnitude and the effect of the gyroscopic torque when the ship pitches bow, that's front, down at a rate of 0.02 radians per second. That's the precessional velocity. The answer is given in the bracket here. I would encourage you to stop the presentation and attempt exercise 1, but I'll show you the full work solution on the following slide. Here's exercise 1, commencement of the solution. We're informed in the question that the ship has an engine that rotates clockwise when viewed from the front. So when viewed from the front of the ship, that's the bow, we can see that the angular velocity omega is in a clockwise sense, hence this double-headed arrow. And we're also informed in the question that the ship pitches bow, that's the front, down. So if the ship pitches bow down, and obviously the stern pitches up, as shown here, which means we draw the second angular velocity vector in this orientation here, having rotated through small angle d theta. So the change in angular velocity is shown by this double-headed arrow here, having descents from the beginning of the vector to the end of the vector. We then can extract the moment of inertia directly given in the question, and the shaft's angular velocity has been converted here from RPM into radians per second. The precessional velocity omega p is explicitly given in the question. So here's the information extracted from the question for exercise 1. So here's my thinking process here. What are we trying to find? We're trying to find the gyroscopic couple, T in this case. What are we given in the question? This time we're given the moment of inertia directly. So I've got my I. On the previous slide we've calculated the angular velocity omega, and we were given explicitly the omega p, the precessional angular velocity. So it's a fairly straightforward solution here. Exercise 1, solution continued. So here's a calculation for the gyroscopic couple or gyroscopic torque. Capital T is I multiplied by omega p. Inserting the values from the previous slide, the applied gyroscopic couple is 209.5 Newton meters. So the gyroscopic couple is in the sense given by this double-headed arrow here. The change in velocity on our velocity vector diagram, that's applied torque T. And if it helps, here's a sketch of the right-hand screw rule showing the rotational direction of applied gyroscopic torque T. If we now consider the effect of the inertia or reaction couple, labelled TR here, that will be in a clockwise sense in what's termed the transverse direction. That's perpendicular to the shaft direction. And again, if it helps, here's the depiction of the right-hand screw rule in the reverse direction. So TR has the same magnitude as T above, but it's in a clockwise sense when viewed from the top of the ship. So here's the view from the top of the ship. When we look down on this rotational vector, we see that TR is in a clockwise sense from the top of the ship. I would encourage you to stop the presentation and just think through for a moment the sense of TR viewed from the top of the ship. Exercise 2. A ship has a turbine engine that's mounted with its axis of rotation lengthwise in the ship. The engine rotates clockwise at 100 revs per second when viewed from the back or the stern of the ship. The effective rotated mass of the engine is 0.9 ton, has a radius of gyration of 50 centimeters. We're asked to calculate the magnitude of the gyroscopic couple that's produced when the ship turns right on a radius of 0.3 kilometers at an angular velocity of 7.92 kilometers an hour. We're asked to state the effect of this couple on the ship's motion. The answers are shown in the bracket here. I would encourage you to stop the presentation and attempt this question, but I'll show you the full work solutions on the following slides. So here's exercise 2, solution. Here's a sketch of our ship. Here's the engine denoted in the ship. We're informed in the question that the engine rotates clockwise at 100 revs per second when viewed from the back or the stern of the ship here. So my omega velocity vector arrow is double-headed as shown. If I put my thumb of my right hand in that direction and view my curved fingers, then they will be going in a clockwise direction when viewed from the rear here. Right hand screw rule for omega shown here. After some increment of time, then the ship has moved on its curved path. So notice both the linear velocity vectors and the angular velocity vectors here have changed their direction. And the question, we're also given the radius, but we will need to calculate the omega p, the precessional angular velocity. So again, let's think through the problem given to us for exercise 2. What are we trying to find? Well, again, we're trying to find the gyroscopic couple and its effects. That means we need to find the moment of inertia, where we're given in the question the effective mass and radius of gyration of the engine. So that means we can actually find I. So we'll have the I value, moment of inertia calculated. We will need to have the angular velocity omega, but we're given that in the question, although it's in revs per second, so we need to be careful of the information given. And we need to find the precessional velocity, omega p, but again we can find that. We have the linear velocity of the ship and we have the radius of curvature. We can find the omega value. So using v is equal to omega r, we can find this value here. Again, if you want to, you could stop the presentation and you could attempt the question on your own, but the full solution follows. Exercise 2, solution continued. So extracting information from the question. The engine speed given is 100 revs per second. So omega is 100 revs per second multiplied by 2 pi. So that's 200 pi radians per second, which is the exact value, or to 2 decimal places, 628.32 radians per second. Notice in the conversion this time only 2 pi was used because the angular velocity is stated in revs per second. So we only need to convert the revs to radians, so that's multiplied by 2 pi. The angular velocity is already in seconds as given. Extracting the engine mass from the question, that's stated as 0.9 tons, so mass actually is 900 kilograms in our calculations. And the radius duration stated in the question is 50 centimeters. So K, 50 centimeters, convert to meters, that's 0.5 meters. Also be careful with the radius of the turn of the ship. So capital R here, 0.3 kilometers, stated in the question, is 300 meters. The linear velocity of the ship, V here, convert into meters per second, that's 7.92 kilometers an hour, so that's 2.2 meters per second. So calculate the moment of inertia, I, inserting the values from above. The moment of inertia is 225 kilogram meters squared. Step 2, calculating the precessional velocity omega p. That's the linear velocity shown above v of 2.2 meters per second divided by the radius of the turn, which is 300 meters above. So omega p is 7.3 recurring times 10 to the negative 3 radians per second. We can now calculate the gyroscopic couple, T, and again inserting the values into the equation for I, for omega, and for omega p. So the gyroscopic couple is 1037 Newton meters. So exercise 2, solution continued. So considering the view from the top of the ship, looking down on the ship here, this angular velocity shown here on our sketch is this angular velocity vector shown here. The double-headed arrows relate to the rotational direction of the engine shaft. And due to the precessional angular velocity omega p, this second angular velocity vector shown here, having moved through angle d theta, is shown here on our velocity vector diagram. So here is the change in velocity vector, again from the end of the first velocity vector to the end of the second velocity vector, indicates the sense of the double-headed arrow. And again, considering the right-hand screw rule, shown here, the applied torque, capital T, is in this direction, based on the right-hand screw rule. So the reaction torque or the inertia torque, TR, has the same magnitude, but it's in the opposite direction. So now here's the right-hand screw rule. So then from applying the above right-hand screw rule, we can see that the torque, TR, produces a rotation such that the bow or the front of the ship dips down, thus the stern or the rear of the ship rises. Of course, the magnitude of the inertia or reaction torque TR is the same as that of T, so it's 1037 Newton meters. Again, I would encourage you to start the presentation and try and think through the effect of the reaction torque on the ship, bearing in mind that we are considering this vector diagram viewed from the top of the ship. So the effect of the reaction torque is bow down. Exercise 3. A motorcycle travels at 80 kilometers an hour around a left bend of radius 30 meters. The motorcycle's wheels have an outer diameter of 0.5 meters, a mass of 2.8 kilograms, and a radius of gyration of 240 millimeters. We've got to calculate A, the angular velocity of the wheels, B, the moment of inertia of each wheel, and C, the magnitude of the gyroscopic torque produced on the bike. We have to predict the effect of this torque on the bike. The answers are shown in the brackets here. I would encourage you to stop the presentation and attempt exercise 3, but again the full solution is shown on the following slides. Exercise 3, solution here. Extracting information from the question, the linear velocity given in the question is 80 kilometers an hour. That's converted straight away into meters per second, so that's 22.2 recurring meters per second. The radius of the track is 30 meters, so track radius R here, 30 meters. The outside diameter is 0.5 meters, so capital D here is 0.5 meters. That means the radius of the wheel is D divided by 2, so 0.25 meters. The mass of one wheel is 2.8 kilograms, so M 2.8 kilograms. And the radius of gyration was 240 millimeters, so K is 0.24 meters. Here's a sketch of the motorbike. It's a plan view shown here. Similar question to that we've seen previously. So let's look at the full solution. Exercise 3 solution is continued here. So part A, we're asked to find the angular velocity of the wheels, omega. So we've calculated the linear velocity on a previous slide. The radius of the wheel is 0.25 meters. So we can calculate the angular velocity, 88.89 radians per second. In part B, we're asked to determine the moment of inertia of the wheel, so that's I. And that's the mass M, 2.8 kilograms per wheel, multiplied by the radius duration squared, so 0.24 squared. The moment of inertia is 0.1613 kilogram meter squared. That's part B calculated. Part C, we've actually got to find the gyroscopic couple. So we need to first of all find the precessional velocity omega p. That's the linear velocity v, 22.22 meters per second. But this time divided by the radius of the bend, capital R here, that was 30 meters. So omega p is 0.741 radians per second. We can now calculate the gyroscopic couple for one wheel, TW. We have the moment of inertia above, we have the angular velocity omega above, and we have the omega p calculated above. So evaluating, that's 10.624 Newton meters. That's the gyroscopic couple for one wheel. Of course, we have two wheels, so we need to calculate the total gyroscopic couple, T here. That's twice the gyroscopic couple for one wheel. So 21.25 Newton meters is the total gyroscopic couple. So exercise 3, the solution continued here. Here's our plan view of the motorbike. And here's the plan view of the vector diagram. Here's the first angular velocity vector shown here on a vector diagram. Here's the second angular velocity vector shown here on the diagram. So that means change in angular velocity has this sense. So here's the direction of the applied gyroscopic couple, T here, on the right hand screw rule. The right hand screw rule for gyroscopic couple T. And as always, the effect of the inertia or the reaction couple, TR, is equal and opposite to the applied gyroscopic couple T. So TR in this case tendencies to turn the bike outwards. It's a view from the rear here. Again, I would encourage you to stop the presentation and think through clearly how we constructed the velocity vector diagram and how we actually determine the senses of T and TR using the right hand screw rule. Let's consider exercise 4. The rotor of a ship's turbine has a mass of 5 tons and a radius of gyration of 500 millimeters. The rotor revolves at 750 RPM in a clockwise direction when viewed from the stern, that's the rear of the ship, and it propels the vessel to 50 kilometers an hour along a curved path of 0.3 kilometers. So that's the radius, 0.3 kilometers. We're asked to determine the magnitude of the gyroscopic couple acting on the vessel or ship due to the turbine, and the effect of this couple if the vessel is turning to starboard, in other words turning to the right. The answers are given in the bracket here. This is a fairly similar problem as posed in the previous exercises, so I would encourage you to stop the presentation and attempt exercise 4, but I'll briefly outline the solution on the following slides. Exercise 4, here's the solution. As always, extract information from the question. The mass of the rotor on the ship's turbine, M, is 5 tonne in the question, so of course that's 5,000 kilograms. The radius of gyration given in the question is 500 millimeters, so again, converting to meters, K is 0.5 meters. The angular velocity of the turbine is 750 revs per minute, so we need to convert that into radians per second. So the angular velocity omega can be specified as 25 pi radians per second, that's the exact value, or to 2 decimal places, that's 78.54 radians per second. We also need to convert the ship's linear velocity from kilometers an hour into meters per second. So V is 13.89 meters per second. That's converting this velocity here, as given in the question. So R here converted to meters, that's 300 meters. That's the radius of the curved path. As always, I encourage you to sketch the problems. This is my plan view of the problem. I'm referring to the question. The ship's turbine revolves in a clockwise direction when viewed from the stern or the rear of the ship. So if this is the engine back here, then the angular velocity vector would be in this direction. You place the thumb of the right hand in the direction of double arrows. Look at the sense of your curved fingers when viewed from the rear, arrow A here. They will show a clockwise direction. Right hand screw rule here shown for omega. Sometime later, when the ship is moved around the curved, the angular velocity vector will change its orientation. In exercise 4, solution continued. I'll let you review this solution at your own pace. Very similar to the previous exercises, we need to calculate the moment of inertia I from the mk squared formula. We have the information to work out I from the question. I'll let you review that at your own pace. We need to work out the precessional velocity, omega p. That's the linear velocity v, which was originally 50 kilometers an hour in the question, which we converted to meters per second, so that's 13.89 meters per second. And that's divided by the radius of the curved path, which was 300 meters. So our precessional velocity is 0.0463 radians per second. We can then calculate the gyroscopic couple or torque from the formula I multiplied by the omega multiplied by omega p. So we can determine the applied torque is approximately 4.5 kilonewton meters. Example 4, solution continued. We now need to consider the effect of the inertia or the reaction couple, usually denoted TR. Actually denoted it TI in this case. Some textbooks use the symbol I for the inertia. As we know, that's going to be equal and opposite to the applied torque T. So consider this plan view here. This would be my omega value, which is this vector shown here on this diagram. This would be the omega at some angle d theta later, shown here on my diagram. So from the vector diagram, here's the direction of the change in velocity vector from the end of the first velocity vector to the end of the second velocity vector. So here's the right hand screw illustration, if it helps, showing applied torque T, shown here on the vector diagram. So in this case, the reaction torque or the reaction couple TR tends to dip the bow or the front of the ship. And again, if it helps, here's the illustration of the right hand screw rule, showing how TR is dipping the bow or the front of the ship. The side view of the ship shown here shows the effects of the applied and reactive torques more clearly. Exercise 5. A solid disc rotor, shown in the sketch here, of mass 20 kilograms and outside diameter 60 centimeters, rotates at 10,000 revs per minute. The rotor sits equispaced between two bearings, labelled A and B in the sketch, bearing A, bearing B, and these bearings are located 1,000 millimeters apart, shown here. If the precessional velocity of the rotor is found to be 120 radians per minute, we've got to determine A, the gyroscopic couple, and B, the force exerted on the bearings, A and B, by this gyroscopic couple. For reference here, we're informed that the radius of gyration of a solid rotor or solid disc, as shown in the sketch here, is given by the formula K is equal to the square root of a half r squared in brackets, where r would be the outside radius of the rotor. The answers are shown in the bracket. The first part of this problem is very similar to that we've considered in previous exercises, but part B does require us to extend the solution. Essentially, once we've found the gyroscopic couple, we simply divide it by the distance between the bearings to find the force on the bearings. I would encourage you to start the presentation and attempt exercise 5, certainly part A to begin with, and if you can, see if you can attempt part B also. I will show you the full work solution on the following slides. So exercise 5, here's the solution. So extracting the information from the question, the mass of the rotor was 20 kilograms. The rotor outside diameter is 60 centimeters, so that's 0.6 meters. And of course the outside radius is half the diameter, so 0.3 meters for the radius. The angular velocity, omega, was 10,000 rpm in the question. We need to convert that to radians per second, so that's 1047.2 radians per second. The precessional velocity is stated in the question, omega p. It was actually stated as 120 radians per minute, so we need to divide that by 60 to calculate radians per second, so that's 2 radians per second. We were given in the question the formula for radius of gyration for a solid disc, shown here. It was actually K is equal to the square root of a half r squared. And if we were to square both sides, we could write that as K squared is equal to a half r squared. And that's essentially what I've done here. K squared is equal to a half of r squared. That's essentially the formula stated in the question. We want to find K squared, the radius above 0.3 squared divided by 2. So that's 0.045 meters squared. We can then calculate the moment of inertia of the rotor I. We know that's m K squared. So inserting the values, the moment of inertia of the rotor is 0.9 kilogram meters squared. We can then calculate the gyroscopic couple for the rotor, the applied couple. T is equal to I multiplied by omega p. Inserting the values from above, the applied gyroscopic couple is 1,885 Newton meters. Exercise 5, solution continued. So here's the velocity vector diagram showing the initial angular velocity, time t is equal to 0. This angular velocity shown here on this view, the angular velocity shown here on this view, and due to the precessional velocity, omega p, the angular velocity rotates through angle delta theta to this orientation, which would be this velocity vector on our diagram. The change in velocity vector is shown here, having descents from the end of the first velocity vector to the end of the second velocity vector after time t is equal to delta t. Using this right hand screw rule illustration, we have the gyroscopic torque applied to the rotor. So on this diagram, if we have an applied gyroscopic torque, we will have an equal and opposite reactive or inertia torque TR. And it's this reactive torque which we will use to calculate the forces applied to the bearings, labelled as FA on bearing A here, and FB on bearing B. On the next slide we'll show how to calculate the forces applied to the bearings FA and FB. Exercise 5, solution continued. So the inclusion of this inertial torque, resisting torque, which is generated through Newton's third law, allows us to now analyse the rotor and bearings statically. And because the rotor is equally spaced between bearings A and B, then force A will be the same as force B in this case. To find the forces at the bearings, labelled FA and FB here, we simply take moments about, in this case, point A. So from our previous lecture on calculating reactions in beams, we use the equilibrium equation. Summation of all the clockwise moments is equal to summation of all the anti-clockwise moments about point A. So in this case, about point A, our clockwise moment would be TR, and our anti-clockwise moment would be the force at bearing B multiplied by the distance between the bearings, called that D here. So inserting the values, the reaction couple is 1,885 Newton meters, distance B is 1 meter. So rearranging, we can find the force in the bearing. It's actually 1,885 newtons due to the geometry used here. So FA and FB from above are the same value. Just specified it in kilonewtons here. Exercise 5, solution continued. So again note that the reaction torque, reaction couple, is effectively an imaginary couple and is only used to bring a dynamic situation into a static situation. We reviewed this principle in a previous presentation relating to D'Alembert's principle and also considering the concept of centrifugal force. I'll leave you with some tutorial questions to work through at your own pace. Here's question 1. A locomotive is travelling at constant velocity on a straight and level track. One of the driving axles of the locomotive has 2 wheels, each with a radius of gyration of 66 centimeters and a mass of 400 kilograms. The wheels are 1.85 meters in diameter, and the distance between the planes of the wheels is 1.5 meters. When traveling at 100 kilometers an hour, the locomotive passes a defective rail that causes the right-hand wheel to fall with a linear velocity of 0.377 meters per second. We're asked to find the maximum gyroscopic torque caused and state the effect that this has on the locomotive. The answer is shown in the bracket here. Just going to provide you with a hint for question 1. Here's question 1, a hint to calculate the angular velocity omega. That will be the linear velocity of the train divided by the radius of the wheel, shown here. And to calculate the precessional velocity in this case, that will be the velocity of the vertical fall of the wheel, shown here as V suffix W, divided by the distance between the wheels, labelled as L here. Once omega and omega p are determined, the rest of the solution is very similar to that of the previous questions. And question 2, I'm going to let you review this at your own pace. It's very similar to the problems we've considered previously. Here's the bibliography used to help generate this presentation, and I hope this has been of interest to you, and thank you for viewing.